Welcome back, everybody, to your Chem 4 lecture, starting off with lecture 2, beginning chapter 2, and today we're going to talk all about measurements. So a big part of science is measurements, and that's going to be part of your professional life as well, where you're going to be making measurements and you're going to be evaluating those measurements based on different criteria, different scales. So what we want to do in the chemistry lab and in the lecture is to set you up with sort of a fundamental understanding of a lot of the units of measurement that you're going to use throughout your professional career, and then also how to make calculations with those measurements. So let's go ahead and get started. So in science and in most health settings, we use what's called the metric system, which is just a series of units that are used to measure things like volume, mass, length, all of these things. And this metric system is related to, but not exactly the same as, the International System of Units, or SI units. The metric system and SI units are very closely related. As you'll see, there's a few things where the SI unit that we would use internationally is either too big or too small for common usage. So we've settled on, for the metric system, a slightly different unit that's related to it. Well, that's just more convenient for everyday use. So these are things for length, volume, mass, temperature, and time. They all have their own specific units that's used within the international system and then within the metric system. There we go. So as we mentioned here, we've got volume in the metric system is the liter. So this should be familiar to you, right? I mean, you buy soda, you get a 2-liter bottle. Well, it's 2 liters. So you get the idea of what that size is there. Now, the SI unit is the cubic meter, or the meter cube. So volume, of course, it's this how much can a container hold, right? Well, a meter cubed, think of a meter, which is the length measurement here. It's about a yard. So a meter cubed would be a cube, the volume of a cube, whose sides are a meter long, so about a yard long. That's a big container, in fact. So that's not the kind of unit of water or the unit of volume that we want to use every day for things like how much do you need to drink, that kind of thing. So it's a very convenient unit for calculations, but it's not a very convenient unit for us to use every day. So that's the idea with the metric system. We're going to use these every day. They're convenient to use. The SI unit, this is kind of the formal scientific unit that can be used to communicate different measurements that we're going to make in the science class. I already mentioned this, but the length unit is the meter. It's related to, but not quite the same as, the yard. We'll have a conversion for you later on in the class, but it's about the same. So you can think in your head, a yard, about a yard, when you think of a meter, and it's the same length. So, of course, length is just how long is something. Mass. So mass, we think of mass in terms of weight a lot of times in the United States, especially. So we think of weight in terms of pounds. Now, the problem with that is that your weight is a little bit different depending on the force of gravity. So your weight on the moon is less than your weight on Earth. Now, that's not very convenient for science, because in science, we like to kind of eliminate all those variables. And so we instead come up with this idea of mass. And that's basically how much stuff is inside of you, or how much stuff is inside your phone, for example. And this mass is consistent, wherever you're measuring it in the universe, whether you're on the Earth, on the moon, in space, whatever. A gram of something is always a gram of something. A kilogram of something is always a kilogram of something. So here you note, again, there's a slight difference here for the metric versus the SI unit. The metric unit is the gram, the SI unit is the kilogram. A kilogram is about 2.2 pounds. So it's, you can think of it, it's just a bigger pound. That's more convenient unit to use if you're measuring like your body weight or something like that. In the lab, we're dealing with stuff that we're kind of holding in our hands. So we use the gram unit a lot in the lab, and a gram is about the weight, or the mass, excuse me, of a paper clip. See, I even think in weight. So, you'll never lose that. For temperature, we use in the metric system the degree Celsius. The degree Celsius is just a convenient way to kind of measure everyday temperatures. right? I mean, outside, it's hot today, but it doesn't usually get above 30, 31 degrees Celsius here, and that's kind of a convenient way to talk every day about temperatures. Of course, if you grew up in the United States, you're probably familiar then with the degree Fahrenheit. The degree Fahrenheit is not used in science classes just because it's not closely related to the SI unit here, which is the Kelvin. The degree Celsius and the Kelvin are very closely related for reasons that we'll talk about in a little bit. Additionally, degree Celsius is kind of easy to grasp. Basically, you take the temperature of freezing water, that's ice, that's 0 degrees Celsius, and you take the temperature of boiling water, that's 100 degrees Celsius, and it's just you cut that into 100 pieces. Well, that's your degree Celsius scale. So it's just very convenient. Two things that we experience every day, whether it's ice, you need to get ice for your cold drink, or if you're boiling water to make pasta or something like that. Now that's not good enough for the SI unit. For the SI unit, we need Kelvin. And this kind of is going to be a longer discussion that we'll have later in the chapter. But the Kelvin is a modification of the degree Celsius scale, where you'll notice we talked about degrees Fahrenheit, we talked about degrees Celsius, but the Kelvin is not a degree scale. That's because it is based on absolute zero. Absolute zero is the lowest temperature possible in the universe. And we'll talk about what that means and how that could be possible. But basically, the zero for Kelvin is absolute zero. So there's no negative Kelvin temperature that you ever have to worry about. Kelvins are always building off of that absolute zero. So that's why it's no degrees. Hopefully that's not too deep right just yet, but we'll talk more about this in a little bit. Time. Now, here's one that should be familiar to you, which is the second. Still the same second. They didn't change it. They thought about changing it, but it was going to be way too complicated. So we're just like, hey, we're just going to keep using the second. Even though it doesn't make any sense, right? It's you take a day, and then it's 24 hours in a day, and then 60 minutes in an hour, and then 60 seconds in a minute. Whatever. I don't understand why that is myself, but whatever. We kept the second just the way it was. So that's convenient. Okay, so starting off with volume. Again, we're going to dive just a little bit deeper into these metric units here. As I mentioned with volume, meters cubed is the SI unit, but that's a huge container. That's like a very big box of, it's quite a large box of liquid. It's not the type of liquid the amount of liquid that you use in a day. So it's not very convenient. So instead we use the liter. So this is a 1 liter water bottle here. So that's convenient because it's like, oh, I drink that. I know I drink a liter of water. In lab, oftentimes we're going to be measuring in terms of milliliters here. So this, for example, is a graduated cylinder. Hopefully, either you will have seen this very soon. You'll see this in the first week of lab. So whether you're watching this before or after. This is going to be a graduated cylinder, and it's going to measure the volume of the liquid inside of it in terms of milliliters. And so it's a very convenient way to measure that. And yeah, just to give you an idea, again, the liter is this here. The milliliter is 1/1000th of this. You know that because liter, you see liter and then milliliter. Milli means 1/1000th. So a milliliter is 1/1000th of a liter. And so it's just a very small volume. So just to give you an idea of like how these are related to some units that you might use, as I mentioned already, 1 liter is equal to 1,000 milliliters. This is something you'll be expected to remember. So just keep this in mind. Now, again, as I mentioned, there's a system for this, so we don't necessarily need to know that. The conversions here, 1 liter is about the same as a quart. It's 1.06 quarts. So if you know this equivalent, then you can actually convert between quart amounts and liter amounts. That might come in handy in the future. And that's something that we're going to focus on a lot in the first chapter is how to convert between units using kind of a systematic method. And then finally, if you need to convert from milliliters to quarts, it's 946 milliliters in 1 quart. Okay, so that's volume. Next up, we have length. So length should be familiar to you. What's the height, what's the width, what's the length of an object. You're probably familiar with a yardstick, using a yardstick or a foot ruler. But I'm sure, I hope that you've seen a ruler that has like maybe the inches and feet on the one side, and then on the other side, centimeters maybe. Well, so that's the units that we're going to be using now, is we're going to be using centimeter units now. Note that we have the SI unit and the metric unit is the meter for both of them. Most frequently, like we're going to be using centimeters when we're in lab, just because think about the things that we're going to be manipulating in lab. They're going to be, things that you can hold with your hands. So of course your hands are not a meter long, just, a few centimeters basically is the idea here. And I'll show you the conversions on the next slide for, centimeters to inches, for example, if you're familiar with that. So a meter stick and a yardstick, very similar as I mentioned. Now 1 meter is actually 39.37 inches. And you'll remember 1 yard is 36 inches. So it's basically just 3.33 inches longer to get to the meter stick. If you're already familiar with the metric units, I apologize. I know this is going to seem dumb. I'm talking, very specifically to people who grew up in the American system and are used to the American system. If you are very familiar with the meters, grams, milliliters, all that, feel free to, you can kind of skip forward a little bit. But, I just want to make sure we're all kind of on the same page. Apologies if it's boring at that point. Okay, so here's our relationships that we're going to need to know for length. 1 meter is 100 centimeters. So just like before where I said 1 liter equals 1,000 milliliters, and we know that because milli means 1/1000. It's the same thing, but for centi means 1/100th. So a centimeter is 1/100th of a meter. Therefore, 1 meter contains 100 centimeters. 1 meter is 39.4 inches. You can also convert that into yards. 1 meter is 1.09 yards. And then finally, we have an exact conversion where we have 2.54 centimeters is equal to exactly 1 inch. And that's a definition. The people who are in charge of inches say, hey, we're gonna base 1 inch equal to 2.54 centimeters. I didn't mention this before. I guess I should have mentioned this before. The whole idea of SI units is that they're standardized. So that means that there's sort of an authority, that keeps these units. And there's some really interesting stories into like how they get there. And actually the most interesting story is with mass. So we'll start here with mass. And I'll tell you a little bit more about these people who keep the units, the keepers of the units. Okay, the mass of an object is how much stuff is in the object. So the mass of an object is a measurement of the quantity of material that it contains. Now you can measure this on an electronic balance. You can also use scales. So I mean, that's kind of, if you ever go to the doctor's office and they have an old non-digital scale where you like step on and then they move the things over. Maybe you're gonna have to do that in the future if you work at some place that only has that type of balance. You're measuring a mass there, and it's just, you've got a balance that's giving you the mass from there. I don't know, that's kind of fun. In lab, fortunately, we're going to be using the electronic balances, so don't have to worry too much about that. The SI unit is the kilogram. Most commonly, we're going to be using grams because, again, just what you manipulate with your hands. A kilogram is 2.2 pounds of something. So, like, we might use a kilogram of water for a certain reaction, but we're not going to be using kilograms of material of other types. So here's our unit conversions. We know 1 kilogram equals 1,000 grams. This, again, this metric system is great because it tells you everything you need to know for the conversions in the name of the unit itself. Kilogram means 1,000. So 1 kilogram is 1,000 grams. Literally, just think kilo takes it to, becomes 1,000. So 1 kilogram is 1,000 grams. It's sort of the opposite of milli, right? Milli was 1/1000th. So a milliliter is 1/1000th of a liter. A kilogram is 1,000 of grams. As I mentioned already, a kilogram is 2.20 pounds. So just to give you an idea, if you're familiar with the American system of measurements of weight, that's your conversion factor there. And 454 grams equals 1 pound. This can be convenient if you're doing recipes in, from other cultures that use the metric system. So from other places, you can just kind of keep these conversions in mind for an easy way to get your recipes right. Now, the kilogram, interesting story here real quick. The kilogram, as I mentioned, is kept by the people in charge of the SI system. They have tried to, or in the past, they have worked on, coming up with a way that they can have a kind of fundamental relationship of a kilogram to some other fundamental part of matter. They did that with time, for example, by counting the number of times an atom will spin, and they'll say, okay, that's the second. They did it with length by saying, 1 meter is the distance that light travels in a certain amount of time. And then it's like, okay, well, so that's based on the speed of light. That's universal. That means aliens could understand what a meter was if we could figure out how to communicate with them. Now, kilogram, though, is very difficult to do that with for all sorts of reasons. We're going to learn about isotopes in the future here. And as it turns out, isotopes are going to mess up the measurements of different atoms, whereas otherwise you might say, oh, you have this many of this type of atom, and that's of 1 kilogram. Well, if you have a different isotope distribution, it doesn't work that way. So they just what they did is they just made a sphere of metal, and they said, okay, this is 1 kilogram, and every 10 years we're going to take it out and we're going to measure it, make sure this is the 1 kilogram that's the same throughout the world. And then they made copies of it, and they gave copies to, there's one in the United States in the National, what is it? The Standards and Measurements Institute, I think, in Maryland. There's several in Europe, all throughout Asia, everywhere across the world. Not every country has one, but there's dozens that are kind of spread throughout the world, and those are sort of the gold the gold standards, I guess. They're not made out of gold, but that is what a kilogram is. Now, what happened is 1 year they took it out of the measurement and they tried to compare it with the other kilograms that were around the world. And as it turned out, they shaved off about 0.000001% of the mass of that sphere. That doesn't seem like a big deal, but what that means is, based on their definition, if 1 kilogram is the mass of that sphere and that sphere changes, well, kilogram just changed around the world. So that would mess up every measurement that's done, the measurements that's done to sell bananas and all that stuff. Like that's, that would change around the world. So that's a big deal. They are coming to some conclusion on this. I need to read up more on it. If you have questions on it, ask me in lab, and I will let you know what the conclusion of that is. But I think it's just been decided now this year. Anyways, temperature. Now, temperature is a real difficult one to come up with because temperature has been kind of measured in a relative way for the longest time, in human existence. It's like you've got, is it cold outside? Is it hot outside? And it was notoriously tricky to measure, such that a good thermometer didn't really show up until the early 1800s on the back of a lot of technology and a lot of work to produce it. So temperature, of course, you think of it as how hot or cold something is. We measure it for the metric system on the degrees Celsius scale. For the SI system, we use the Kelvin scale. Now, I already mentioned here that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. That's the equivalent of 32 degrees Fahrenheit for the freezing of water and 212 degrees Fahrenheit for the boiling of water. And I also mentioned here the Kelvin scale. The reason it's not a degree scale is that it begins at absolute zero. 0 Kelvin is the coldest temperature that is possible. Okay. Yeah, anything else I want to say here? I think you get it. There's going to be some ways that we convert from one temperature scale to another, and we'll cover that here very shortly. Okay, so finally we have time. Time, as I mentioned, is based on an atomic clock. So it's about the certain number of, I want to say it's based on the spin of an atom. So it's like how much does an atom spin in a given amount of time. Of course, it's a huge amount of time, a huge amount of spins per 1 second. But that's how we are able to say, hey, this is 1 second. Now we're familiar with time, of course, because we use time throughout the day. And then the other measurement would be just using a stopwatch. So for example, in class, we'll use a stopwatch to time a reaction. And so you start at 0, time ticks on, and then after 60 seconds. Okay, now it's done. We've measured our time in terms of seconds. Okay, so here we go. Sample exercise number 1. For each of the following, indicate whether the unit describes length, mass, or volume. So we're going to go through A, B, C, and D, and you're going to tell me, hey, does that mean a length? Is that a mass, or is that a volume? And we're going to pause the video. And when we come back, we'll have the answers up on screen. And oh, right, I almost forgot. The sample exercise packet is available in a PDF down below. I'm also going to have a few printed copies available in lab. So if you just come up to the front of lab, I'll have copies available up there. Hopefully I'll have enough. I don't know who prefers, using digital copy versus physical copy. If you prefer a physical copy, make sure to let me know. I'll have that printed out for you at lab. Okay, well, let's go ahead. We're going to pause the video now. And when we come back, we'll have the answers up. So go ahead, pause. Okay, so looking at the answers here, a bag of onions has a mass of 2.6 kilograms. Well, it's saying right there mass, so I hope you knew that was mass. A person is 1.7 meters tall, that's a length. Medication contains 0.50 grams of aspirin, that's a mass as well. And then finally, a bottle contains 1.5 liters of water, so that's a volume. Okay, next up for sample exercise 2, go ahead, look and find the SI unit for each of the following. We got volume, mass, length, and temperature. Go ahead, pause. And this is going to be a memorization thing. So obviously you'll need to, learn to use these units in the future, but just so you know what those are, go ahead and look them up now. Pause the video. When you come back, we're going to have the answer. Pause. Here we go. So the SI unit for volume, cubic meter. For mass is the kilogram. For length is the meter. And then finally for temperature is the Kelvin. Okay, so next up, we're going to go ahead and identify a measurement that's given in an SI unit. So basically, when we answer these questions, find the one that's given in an SI unit. So here, A, John's height is, you have a choice of 1.5 yards, 6 feet, or 1.9 meters. Well, a yard and a feet, those are American or imperial measurements, depending on what you say. So a meter, well, that's the SI unit, so that's going to be the SI measurement. Go ahead and do that for B and C, and then when you come back, we'll have the answers up on the board. Pause. And we're back. As we mentioned, John's height, 1.9 meters. The mass of a lemon, 0.145 kilograms. Temperature is 255 Kelvin. Now that might seem a little weird, maybe used to using Celsius or Fahrenheit for everyday temperature measurements, but this is what we use Kelvin for. Kelvin's very important in terms of scientific reasons. There's a lot of reasons or a lot of calculations you can only do with Kelvin temperature that you can't do with Celsius or Fahrenheit. So that's why we kind of emphasize the use of Kelvin for the SI unit. Okay, now, one of the most important things I'm going to teach you this semester that's going to affect your future, and so this is going to be one of the things that I'm going to test you on many, many, many times, is basically how to measure a number. So I know that sounds foolish, but based on the tool that you have, the instrument that you have, you can only get so much information from that instrument. So when you take a ruler could be a measuring tool like this. You determine a quantity, length, mass, et cetera, and these numbers are what we call measured numbers. Now, there's a crucial thing with this measured number. So, okay, so let's go through the slides here. So if you're going to report the length of an object, you need to go ahead and look at the values of the marked lines, at the end of the object. So if we go back here, we all agree that the length of wood here is between the 4 and the 5, right? So that means that it is at least 4 centimeters, but it is not quite 5 centimeters. Next, now this is the key part. You need to estimate a last digit by using your tools of estimation, your ability to guess as close as possible how close it is between the first part and the last. That estimated number is the final digit that's going to be reported. So looking here, we would agree that, again, we would all agree that this is at least 4 centimeters long. It's between 4 and 5 centimeters long. But that's not good enough, right? Now to measure it, we need to estimate one digit farther. So we have the ones digit, that's the 4. Now we need to estimate the 10th digit. So we have to guess, well, it looks like it's about halfway, right? So halfway from 4 to 5 would be 4.5. So we'll report it as 4.5 centimeters. Now, if instead the length of wood was here, let's say, well, that looks like it's maybe 20% of the way. So we'd say 4.2 centimeters. Now, here's what's crucial. You can, if the length of the wood is here, you can only say 4.2 centimeters. You cannot say 4.25 centimeters. That would add a 100th digit. That adds a whole other level, and we don't have that. We don't have that unit here on the ruler. So you get your certain digits from the ruler, and then you estimate one more digit, and it's only that one more digit that you can estimate. Think about it this way. Would you believe me if I say, okay, this is 4.5 centimeters? That makes sense based on this ruler here. Now, what if I said this is 4.5237247 centimeters? Would you believe me? Can I see that based on this ruler? No way. You can only estimate, approximately how far it is between the 4 and the 5. And so this is something we're going to work on a lot in lab. And it's something that you should work on as well at home. And, using your book, there's some good examples in your book as well. Okay, now, let's get a better ruler, right? That ruler stunk. This ruler is much better. This is more of a standard ruler where now not only do we have the large markings for the centimeters, now we have the 10th of a centimeter markings as well. So there's 9 markings in between each of the centimeters. And so now we can see, okay, well, we now know for sure that the length of wood is between 4.5 and 4.6. Now, to me, this looks like it's a little bit closer to the 4.6 than it is to the 4.5. So I would say this is like 4.56 or 4.57 centimeters. And I would accept either of those answers. I would also accept what the book says, which is 4.55 centimeters. There's a degree of error, a degree of uncertainty with this estimated digit, but that's okay because it gives us a little bit more information, and that little bit more information is going to be important for the future. So, okay, so the previous ruler only had markings at the ones digit, is the way you can think about it. That means we need to estimate one digit farther, which is the 10th digit. This ruler, a better ruler, now has marking at the 10th digit. That means we have certain digits, the ones digit and the 10th digit, and now we estimate the 100th digit. And this can go on and on. So now in this case, if we had an exact line here, if it ends exactly at the 3 line, then you can say, so in this case, it ends exactly at the 3 line. So you might just be tempted to say 3 centimeters, but remember, we need to estimate one digit farther. So we would say 3.0 centimeters. And that would be our measurement here. Yeah, basically don't forget the 0. Things can also be 0.0, for example. Okay, this is a big one. Sample exercise 4. I mentioned this is going to be very important. So go ahead, give me the length of the red line. So this is going to be difficult to kind of read here, but this ruler is basically, this line is 8, 8.5, 9. So, and then note here, it's like 9.1, 9.2, 9.3, 9.4, 9.5, 9.6, 9.7, 9.8, 9.9, and 10, 10.0. So, okay, so tell me, what is the length of the red line? Based on what I told you, go ahead, pause the video. And when you come back, we're going to explain it out. But I want you to think through it first and try to get the answer right first. So go ahead, pause. Okay, so remember, the thing that you need to check for the ruler is what digits does the ruler tell you? And you're going to need to estimate one digit farther. So for me, like, check it out. So we know the ones digit for sure, right? So we know the ones digit. but we're also given the tenths digit, right? Because we have this 0.1, 0.2, 0.3, 0.4, etc. So we have the ones in the tenths digit. That means we need to estimate the hundredths digit. Well, this line looks like it's exactly on the 0.2, 9.2. So that means it should be 9.20. So I would say the correct answer is 3, 9.20. Now, if you have any questions on that, we're going to take a bunch of time on this in lab, but I want to make sure that you practice this when you get to lab as well. So make sure if you're having any problems at all, come up to me in lab and I'll help show you, using the ruler that we'll have there in person, what that looks like. Okay, now the whole point of understanding measured numbers is basically like in science, and this is what's going to be important in health as well. You need to separate information from non-information. So there's information, that's what's important, and then there's things that we don't know, non-information. And that's the goal of a good scientific measurement. The measurement should preserve what we do know and not taint it with stuff that we don't know. So this brings up our, this is a core chemistry skill. This is going to be a core skill, across the sciences, which is significant figures. So we say that, and significant figures, basically implies the existence of insignificant figures. And that, again, gives the dividing line between information and non-information, stuff that doesn't make any sense, that's not going to contribute any information. Significant figures are all of the digits, including the estimated digit. And so, for example, when we get here 9.20 centimeters, we would say that this measurement has 3 significant figures. The ones digit, which is a 9, the tenths digit, which is a 2, and the hundredths digit, which is a 0. Now, when you're given a measurement, you may be asked to figure out how many significant figures are there in this digit. So we have a set of rules that will tell us that. We have the first rule, which is that any non-zero number in a measurement is a significant figure. Now, zeros is where it gets tricky. Depending on the location in the number, zeros may or may not be significant. So we have 3 different locations for zeros where they can be, and then 3 different kind of rules or applications for it in that case. Okay, this looks pretty scary, but it's not going to be that hard. Okay, so here we go. So look at this. A number is a significant figure if it's not a 0. That's what we already said, right? Any non-zero things are significant. So if we had a measurement 4.5 grams, we would say that that has 2 significant figures because the 4 and the 5 are both significant. Same thing with 122.35 meters. That's 5 significant figures because the 1, the 2, the 2, the 3, and the 5 are all significant. Okay, now here's where things get a little tricky because we're going to talk about zeros. We know that zeros that are between non-zero digits, these are what we call internal zeros. These internal zeros are significant. So 205 degrees Celsius is a measurement. There's a 0 between a 2 and a 5. The 2 and the 5 are both significant. So therefore, the 0 is significant as well. So 205 degrees Celsius, that's 3 significant figures. 5.008 kilograms, same deal. We have 2 internal zeros here. So those are both going to be significant. Okay. C. So internal zeros, yes. Next up, we have a 0 at the end of a decimal number. So this is the 0 at the end of a number that contains a decimal point. And wow, I already see a mistake. Wow, okay, so hold on. Let's fix this right now. 50 point, there we go. All right, that's much better. So a decimal number means a number that contains a decimal point. So in this case, we have a 0 that's at the end of the number. And this number has a decimal point. So that means this is a significant 0. Same thing here, 16.00 milliliters. These zeros are what we call trailing zeros. They're at the end of the number. And that number contains a decimal point. So in both of these cases, these zeros are going to be significant. So in this case, the 1, the 6, the 0, all significant. The 5 and the 0, all significant. And then D is kind of a subrule of C. Basically, it's saying you have a trailing 0 at the end of a number in scientific notation? Yeah, so, okay, so 5.70 times 10 to the negative third, that zero is significant, but you already knew that because of C. It's at the end of a decimal number. Crucially, for scientific notation, it doesn't change the number of significant figures. That is never going to change. The only thing that's going to change is basically how you write them. Okay, so 2 rules for zeros so far. Internal zeros are significant. Trailing zeros at the end of a decimal number are significant. That means that we have these other cases that are not going to be significant. So the first example is a leading zero. If there's ever a zero in the front of a number, so before the first non-zero digit, that means that zero is just a placeholder. It's just telling you how far you have to get till you get to the actual information. That is not significant. So if we took the number 0.00004 seconds, that measurement has 1 significant figure. These leading zeros at the beginning of the number are not significant. Same thing with 0.075 centimeters. In this case, we have 2 significant figures. We have the 7 and the 5, but the leading zeros here, not significant. So leading zeros, never, those are zeros at the beginning of a number, never significant. Finally, if that zero is used as a placeholder at the end of a number without a decimal point, then it is also not significant as well. So here we have this number, 850,000 meters. Well, these zeros here, there's no decimal point here. So that's telling us that these trailing zeros in a number without a decimal point are not significant. So I count 1, 2 significant figures. Sure enough, 2 significant figures. 1,250,000 grams. Similarly, no decimal point. That means we only have these 3 significant figures, the 1, the 2, and the 5. Okay, so wrapping up, zeros will be significant when they are internal. In other words, they're between 2 significant figures. They will be significant when they are a trailing zero that's at the end of the number with a decimal point. So there's a decimal point in the number, and there's a trailing zero. That's significant as well. They will not be significant when there are leading zeros. In other words, they're at the front of the number. And also, when they're at the end of a number, the trailing zeros in a number without the decimal point. So this sounds like a lot, but actually when you start to apply these rules, it'll go pretty quick and you'll get pretty good at it. So remember, all non-zero numbers in a measured number are significant. So 38.15 centimeters, that has 4 different significant digits. 5.6 feet, that's another measurement, 2 significant figures. 65.6, 656, those are all significant. And 122.55, that's 5 significant figures. Internal zeros are significant. 50.08 kilometers, that's 4 significant figures because you have 2 zeros in between a 5 and an E. So 201 minutes, the 0 is in between a 2 and a 1. So again, we call it an internal zero. So that then has 3 significant figures for that measurement. If they're at the end, they're a trailing decimal. They're a trailing zero at the end of a number with a decimal. And hold on, there's another mistake here. Apologies for that. So here we have 200 minutes, 200 with a decimal point. That means that these zeros are significant. So we have 1, 2, 3 significant figures. 40.00, we have 3 trailing zeros in a number with a decimal point. So that means that all of these are significant. So we have 4 significant figures for 40.00. Okay, now zeros at the beginning of a number are not significant. So 0.440 kilometers only has 3 significant figures. We have the 4 and the 4, obviously. We have the trailing 0, which is at the end of a number with a decimal. So that's significant as well. But our leading 0 is not going to be significant at all. So 4, 4, and 0, that's 3 significant figures. 0.022, well, these 2 zeros are leading zeros. That means they're just placeholders. They're telling us where the information comes, but they're not containing any information themselves. So that means 0.022 has just 2 significant figures. Similarly, 0.003 has just 1 significant figure. So hopefully this is making sense as a division. These are leading zeros. The leading zeros are never significant. The trailing zeros are significant in numbers that have a decimal point, and they're not significant in numbers that don't have a decimal point. So, and this is the last part here, where trailing zeros in numbers without a decimal are not significant. So 44,000 kilometers contains just two significant figures because we don't have a decimal here. And that tells us that these are not measured zeros here. 810 centimeters, very similar. We just have two significant figures and then a zero that's just acting as a placeholder. Okay, and then note the same rules apply for scientific notation. But you notice basically any zero in this coefficient is going to be significant. So 4.90 times 10 to the third, the same rules apply, but this zero, is a trailing zero in a number with a decimal point. So that means it is significant. So 1, 2, 3 significant figures. 8.0 times 10 to the negative third kilograms. Sure enough, that's two significant figures because this trailing zero is in a number with a decimal point. 6.0330, all of these zeros are significant. The first one's internal, between a 6 and a 3. And then the last one is a trailing zero in a number with a decimal point. So that's 5 significant figures there. So yeah, so this is kind of one of the big benefits of using scientific notation is that scientific notation is only going to contain significant figures. You're not going to have insignificant figures in a scientific notation coefficient. So like, for example, if we had a measurement of 500 grams and we knew that it had 3 significant figures, well, that means that these two zeros are significant, like they're written here with this decimal point. So then when we write this number in scientific notation, it has to be 5.00 times 10 squared grams. That basically, again, tells us that these zeros are significant. Yeah, if we have 400,000 meters with no decimal, that means that none of these zeros are significant. So when we write the number in scientific notation, the only significant figure is going to be the 4. So this becomes 4 times 10 to the 5th meters. Finally, over here, 0.30 centimeters. Well, the leading zero is never significant, right? So when we write this in scientific notation, we know that it's going to be 3 and then point. Well, is this zero significant? It sure is, right? It's a trailing zero in a number with a decimal. So that is a significant zero. That means that we're going to write it 3.0 times 10 to the negative 1 centimeters. Okay, here's what we're going to do. This is a longer sample exercise, but I'm going to help you out with it. We're going to walk through it ourselves. And the question here is, identify the significant and non-significant zeros in each of the following numbers. Then write each number in the correct scientific notation. And we have 3 different numbers here. A is 0.002650 meters. Then we have B, which is 43.026 grams. And then finally C, which we have 1,044,000 liters. And just note where those decimals are and what that's going to mean for your numbers. So go ahead, pause the video. When you come back, I'm going to have my writing board set up here, and I'll show you how I think through these questions, and hopefully that'll help you with the answers. So let's go ahead, pause the video. I'll be right back. Okay, let's go ahead and give this a shot. So starting with A, we've got 0.002650. Okay, so we know the 2, the 6, and the 5 are all significant, right? So that leaves us with the zeros. Now, what's the case for the leading zeros here? Are those significant or not? Well, they're in the front of the number, right? So they're not going to be significant. Now, I mean, eventually they're going to be placeholders, so we'll need that information for the future, but it's not important now. Now, here's a trailing zero. What's the rule for trailing zeros? They're significant when there's a decimal in the number. Do we have a decimal? Sure enough, we do. So that means the zero is going to be significant. So that means that when we write this in scientific notation, it needs to be the 2, the 6, and the 5, and the 0 all have to be there. So let's go ahead then write it in scientific notation. Well, we take the decimal, we move it 1, 2, 3 places to the right. That gives us 2.650 times 10. Now we move the decimal 3 places to the right. So that means it's going to be to the negative 3. Remember, if we move the decimal to the right, that's a negative exponent. If we move it to the left, that's a positive exponent. Okay, next step, 43.026 grams. Well, we got the 4, the 3, the 2, and the 6 are all significant. This 0 is between a 3 and a 2. That's an internal 0, so that's going to be significant as well. Hey, they're all going to come along. That's great. So then let's convert it into, oh, and sorry, this should say meters here. They're measurements, so it's very important that we keep the units with the number. Let's go ahead and turn this into scientific notation. We need to move this decimal one place to the left this time. So that gives us our coefficient, 4.3026 times 10. And we moved it 1 to the left. So that's going to be a positive 1 as our exponent there. And that's it. Easy enough, right? Oh, and it's grams. Sorry. All right, last, we have 1,044,000 liters. Well, let's go ahead and evaluate our significant figures first. So we have the 1, of course, is significant. The 4 and the 4 is significant. We have a 0 that's between a 1 and a 4. That's an internal 0. So that's definitely significant. Now we have trailing zeros. Now, are these trailing zeros significant or not? Well, in this case, these trailing zeros are in a number without a decimal point. So that means that they are not significant. Remember, up here, we had a decimal. So this trailing 0 was significant. Down here, these zeros, no decimal. So it's not significant. Okay, so that means that when we make our scientific notation number, we just need the 1, 0, 4, and 4. All right, now let's move over our decimal point. 1, 2, 3, 4, 5, 6 places to the left. That gives us our number here, 1.044 times 10 to the, well, we moved it 6 places to the left, so that's a positive 6. So 1.044 times 10 to the 6th power. Okay. All right, so I hope that made sense. Oh yeah, so we got all these here. Oh yeah, and we're supposed to come up with the number 4 significant figures, 5 significant figures, 4 significant figures. So hopefully that starts to make a little bit of sense here. Now there is a little bit of a curveball here, which is some things are not measured. Some things are what we call exact numbers. And for these exact numbers, significant figure rules don't apply. Basically, like an exact number is going to be something where, oh, you count up a certain number of objects. Well, that's exactly that number of objects. So 8 cookies, for example, that's not a measurement. You just counted, I have 8 cookies, and that's exactly 8 cookies. There's not a half cookie, you know, you don't have to think about it in that terms. Or 2 baseballs, that's even easier. You just have 2 baseballs. Can't split that into 2.0127 baseballs or something like that. And these exact numbers, you know, the significant figure rules don't apply that we're about to talk about. The other type of exact number that there is what we call a definition. A definition is something that compares 2 units that are within the same measuring system. So like 1 foot equals exactly 12 inches. That's a definition. That's an exact number. 1 kilogram equals exactly 1,000 grams. That's a definition. That's an exact number. That's not a measure. You know, the normal rules of significant figures aren't going to apply to that situation. So like these just give you some examples. You know, you might say there's 5 people. Well, 5 people, it's an exact number. Or 5 capsules. Let's say that you're measuring out a medication in a pharmacy. Well, 5 capsules of medication, you can count that number. That's exactly 5. That's not something that you need to take the mass of to figure out. That's something that you're going to use as an exact number. Okay, so hopefully that makes sense. This is what sample exercise 6 is for. We just want to figure out, are the following numbers measured or exact? And if it's measured, give me the number of significant figures that there are. So we have 3 coins. The diameter of the circle is 7.902 centimeters. Then we have 60 minutes equals 1 hour. Go ahead, pause the video, come up with the answers here. Are they measured or exact? And then give the significant figures if it's measured. Pause it, and we'll come right back. Okay, hopefully you're back. 3 coins, that's a counted number, so that's an exact number. The diameter of a circle is measured, right? 7.902 centimeters. So that's going to be a measured number. And it's measured to 4 significant figures. And then 60 minutes is by definition 1 hour. So that's also an exact number. That's an exact conversion between 2 units. Okay. All right. So here we have another sample exercise. And in these, I just want you to give me the number of significant figures that there are in each of them, A through D. Go ahead, pause the video. When you come back, we'll have the answer for that. So go ahead, pause. Let's say you're back. 0.030 meters, that contains 2 significant figures, right? We know the 3 is significant. These leading zeros are never significant. And then this 0 is significant because it's a trailing 0 and a number with a decimal. Okay, 4.050, the 4 and the 5 obviously are. And then between the 4 and the 5, we have an internal 0. That leaves us with a trailing 0. Now this trailing 0 is in a number with a decimal. So that means that it is significant as well. So that's 4 significant figures. Down here, 0.0008 grams, 8 significant, but these are all leading zeros. These leading zeros are not significant. That's just a 1 significant figure measurement. And then finally, 2.80, we have the 2 and the 8. And then this 0 is a trailing 0. It's at the end of the number, and a number with a decimal. That's significant. So we got 3 significant figures there. Okay. Continuing on with our sample exercises. So here it's basically just like A is which answer contains 3 significant figures. B is all the zeros are significant in which number. And then C is number of significant figures in this number is. So go ahead and answer these questions and pause the video. So pause the video, answer these questions. When you come back, we're gonna go through the answers together. Let's go ahead, pause. Okay, so for A, which answer contains 3 significant figures? Well, 1 is 4, 7, and 6. The leading 0 is not significant, but the trailing 0, it's a trailing 0 and a number with a decimal. So that is significant. Here we have the 4, the 7, and the 6, number 2, and we have leading zeros. Those are not significant. So 2 looks good. And then 3, we have a 4, 7, and 6 again, but we have an internal 0. That's significant. So that has 4 significant figures, 4 significant figures, 3 significant figures. So the correct answer is 2. All of the zeros are significant in this one here. So, okay, so 0.00037. So we have the 3 and the 7 are significant. This 0 is significant, but we have 3 leading zeros. That's not significant, so can't be number 1. 25.300. So we have the 2, well, okay, so we're just looking at the 0. So we have a 2, the 5, and the 3. And then we have a 0 and a 0. Well, these are both at the end of a number with a decimal. So I would say they are significant. Okay, and then finally, 2.050 times 10 to the third. Well, the 2 and the 5 are significant. Internal 0 between the 2 and the 5. Then we have a trailing 0 in a number with a decimal. So also the other way we know this is that this is in scientific notation. And by definition, if it's in scientific notation, all of these have to be significant figures. So that tells me that 2 and 3 both have all of their zeros significant. And then finally, the number of significant figures in this number is we have 5 and an 8. And then we have a 0 at the end of a number with a decimal. That's 3 significant figures, so it should be 3. There we go. Okay, so, oops, hold on. Oops, sorry, I pressed the wrong button here. There we go. Okay, so one thing that we're going to need to do, kind of a skill that we're going to need to have this semester is rounding. So this might seem a little foolish, but it's something that you're going to have to do a lot this semester. So it's good to just kind of get some practice at it now, and that's what we're going to start with here. So remember that calculated answers are going to be rounded off, is what we're going to learn about significant figures here. And we have to use these rounding rules to make sure that we have the correct number of significant figures in our answer. Okay, so the rules for rounding haven't changed, basically. Once you know what digit you need to round to, if the first digit that you're going to drop is 4 or less, then you simply eliminate it and all of the following digits. However, if the first digit that you're going to lose is 5 or greater, then the last retained digit is going to be increased by 1. So let's say that we had the number 8.4234. And let's say we wanted to round it to 3 significant figures. So the first three significant figures are going to be the first three. So 8, 4, and 2. So for three significant figures, we look to the right, we see it's a 3, that's less than 5. So that means we're just going to drop this off. And the correct answer to three significant figures would be 8.42. Two significant figures, very similar. The only thing is going to be, this time we're going to stop at the 4. So we stop at the 4, we look next, there's a 2, we drop the 2, the 3, and the 4. We end up with an answer of 8.4. Now, let's say that we're going to round 14.780. If we round it to three significant figures, what that means is you're going to take the first three significant figures in the number. That would be the 1, the 4, and the 7. Okay, that means we need to chop off the 8 and the 0. So that means we take the 7, look to the right, it's an 8. That's higher than 5. That's 5 or greater is what I would say. And that means that we need to actually increase the 7 to 14.8. On the other hand, if we say that we're going to keep just two significant figures, that would be the 1 and the 4. So now we look across, we see that the next digit is a 7. Well, that's greater than a 5. So that means we need to increase the 4 to a 5. It becomes 15. Okay, so next up, we've got 3256. So 3,256. If we're going to round this to three significant figures, keep the first three, 3, 2, 5. Look to the right, it's a 6. That means we're going to round it up. So it should be 3260. Make sure that you keep that placeholder there, right? The ones digit didn't go away. It just is that it was a 6, and now we rounded it off. So it's just rounded to the tens digit is what we would say. Same thing here, if we were to keep it at two significant figures. Well, that's the 3 and the 2. We look to the right, it's a 5. That tells us to round up. So that means that this 2 becomes a 3, and these here just become zeros. So that would round to 3,300. In this case, you drop the 5 and the 6, but it's important to note that you're keeping those digits as placeholders, right? The tens and the ones digit both become placeholders, zeros. Okay, so now why don't you give it a shot? Make sure that you're on the right track here, and then we'll go over it together. Round 3.145 grams to three significant figures for A, and then to two significant figures for B. And then we will give it a shot. So go ahead, pause the video. Okay, so for A, 3.145, rounded to three significant figures. Take the first three significant figures, 3, 1, and 4. Okay, to the 4, we look to the right, it's a 5. That means we need to round up. So that becomes 3.15. Easy enough, right? Okay, now 3.145 to two significant figures. That means we're going to keep the 3 and we keep the 1. From the 1, we look to the right and we see in the hundredths digit there a 4. That's less than 5. So that means we're going to drop it all together, and that becomes 3.1. Okay, I hope that makes sense. If you have any problems with that, make sure that you track me down in lab or office hours, and I'll help you go through some of these practice problems because we're going to keep doing it and keep doing it. So, okay, so now for sample exercise 10, given these calculated answers, go ahead and give me the answers that are rounded correctly to three significant figures. So go ahead, pause the video, work on sample exercise 10, and then we're going to go over the practice problems together. So go ahead, pause. Okay, so to three significant figures, we have 824.75. Well, we have 8, the 2, and the 4. Those are going to be our three significant figures. We look to the right, it's a 7. So that's greater than 5. That means we need to round up the 4 to a 5. So that then becomes 825 centimeters. Okay, 0.112486. Remember, this leading zero is not significant. So we're going to start with the 1, and the 2 as our three significant digits. Look to the right, it's a 4. That means we're going to drop all of this. So this becomes 0.112 grams, just like that. This is a trick question here, 5.3 liters. So we have two significant figures. Need to add in a third. Well, that third is just going to be a 0. It's 5.30 liters. This is going to happen occasionally on your calculator. Your calculator is not going to know significant figures, so it's going to drop them. You're going to need to know significant figures to make sure that you don't miss those problems. Yeah, and that just gives you your answers. Oh, whoa, oops, where'd we go? Lost it. There we go. Hello. All right, we're back. Okay, so that was sample exercise 10. Okay, now, okay, I recommend go ahead and pause. Now, I probably should have cut this up a little bit into smaller lectures, but I realize now is a good time to pause, take a drink of water. We're going to talk about calculations with significant figures in the end of this lecture here. This is something that's very important that you're going to use both throughout the rest of this class and then on into your professional life as well. So this is something that's very important and very valuable. So I'd pause, take a drink. All right, and let's go ahead and tackle this together. Okay, now the thing is, the rules for multiplication and division with measured numbers are a little bit different than what you're used to for multiplication and division with just the math numbers that you have. So it's not just going to be your calculator telling you everything you need to know. You're also going to need to think about the numbers you're putting into your calculator and then think about the numbers that come out of your calculator to make sure that you have the correct answer. Now, the physical operation of a calculator is going to remain the same. So let's say that we have, these are all measured numbers, and we want to do the operation 2.8 times 67.40 divided by 34.8. Well, you can just plug that into your calculator. 2.8 times 67.40 divided by 34.8. And yeah, sure enough, it gives you an answer. That's the correct answer. However, here's the thing. The numbers that we are using are measured numbers. And there is a degree of uncertainty in each of these measurements. So 2.8, we only know that to the 10th digit. 67.40, we only know that to the 100th digit. We don't know anything beyond the 100th digit. 34.8, again, we only know to the 10th digit. We don't know anything beyond the 10th digit. So there's information, and then there's just a lot of uncertainty as well. So like when we take an estimated digit, multiply it by another estimated digit, there's a lot of misinformation that gets kind of like rolled in. So we set these significant figure calculation rules to make sure that we only preserve the information that we know from our measured numbers. So here's the deal. Multiplication and division. When you get your answer, what you're going to do is go through your measured numbers, count up all the significant figures. So here, so 2.8 has 2 significant figures. 67.40, that's 4 significant figures. And 34.8 has 3 significant figures. So here's the rule. Your answer can only have as many significant figures as the measured number with the fewest significant figures. So 4, 3, and 2, one of our measured numbers that we used in our calculation only had 2 significant figures. That means that regardless of what we got on our calculator, our answer can only have 2 significant figures. So this is what shows on our calculator here, but we can only have 1, 2 significant figures. So that means we need to round it. And when we round it, we get the correct answer here of 5.4. Now I know what you're thinking. This seems like you're leaving a lot of information on the table. That's not the case. Remember, this stuff is all like estimated digits multiplied by estimated digits. There's no information in here. This is all just gobbledygook. There's not actual information. It just looks like there's information there because it's numbers, but we don't know anything about these digits. So it's better to leave them empty and not give the impression that we know anything about them. That's the whole point of significant figures. Okay, so now here's a situation that's going to occur for you throughout the course. If you take a number with 3 significant figures, like 8.00, divided by a number with 3 significant figures, like 2.00, your calculator doesn't know significant figures. So your calculator display shows 4. You need to add in the significant figures, 1 and 2. So you're going to have zeros here at the 10th digit and the 100th digit. And the correct answer would be 4.00. But the key thing is understanding, okay, I divided a number with 3 significant figures by a number with 3 significant figures. my answer has to have 3 significant figures. Okay, sample exercise number 11. Give it a shot. We're taking 5.00 centimeters, multiplying it by 3.408 centimeters, dividing it by 2.0 centimeters. Tell me, what is the answer to this question to the correct number of significant figures? I want to give you a shot. Just give it a shot. So pause the video now, give it a shot. We're going to answer it together, but I want to make sure that you have a chance to try to do this on your own here using the rule that we just talked about. So go ahead, pause the video. Okay, hopefully you're back. You've got the correct answer. Let's go through it together. So first off, this is easy enough. You have your scientific calculator. Use your scientific calculator. It's 5.00 times 3.408 divided by 2.0. So in my calculator, when I do all of that, I get 8.52. Okay, now let's check our units here. We have centimeter times centimeter divided by centimeter. So one of these centimeters is going to cancel. The correct unit here should be centimeters. Okay, so 8.52 centimeters. Now, is that correct answer? Well, we have to check significant figures. So 5.00 centimeters, that has 3 significant figures. 3.408 centimeters, that has 4 significant figures. 2.0 centimeters, that has 2 significant figures. So how many significant figures can our answer have? Just 2. Can only have as many as the fewest of the ones that we put into our calculator. So that's 1, 2 significant figures. Look to the right, it's a 2. We drop it. Correct answer, 8.5 centimeters. Yeah, and it should just be centimeters. It shouldn't be centimeters cubed here, because centimeters times centimeters divided by centimeters. Okay, now here's the thing. Hopefully you're really good at that multiplication division rule, but there's a problem. Okay, so that multiplication division rule is pretty easy. I think it's very easy to learn, and it's actually easier to use than the addition subtraction rule. So in the future, when you do addition subtraction, you're going to be tempted to use the multiplication division rule for significant figures. I'm begging you, do not do that. Don't do it. Get ready for it now. In the future, addition subtraction, use the addition subtraction rule. All right, so let's go ahead and talk about that rule now. Now, in addition and subtraction, the final answer is going to be written so it has the same number of decimal places as the measurement having the fewest decimal places. Or you could also say that it's rounded at the unit based on the measurement that has the highest degree of uncertainty. So this works both ways. So let's hear. So 2.012, we know that that is to the thousandths place. 61.09, that's to the hundredths place. 3.0, that's to the tenths place. Well, our answer here, we know that we can only have one uncertain digit, but 3.0 gives us uncertainty in the tenths digit. The 9, that's uncertain in the hundredths digit. The 2, that's uncertain in the thousandths digit. So we have 3 uncertain digits here. We can only have 1. So that means that this, whatever the highest one that's uncertain, has to be the one that we keep. So we're going to keep the 1 here that's uncertain at the tenths place, round it, and it should be 66.1 in this case. So again, either way you want to think about it, basically your answer can only have the one uncertain digit. And that one uncertain digit has to match the biggest uncertain digit from the biggest uncertain decimal place from the answers that you added or subtracted together. So in this case, it was the tenths place. That means that we can only have the tenths place in our answer. Example number 2. 65.09 minus 3.0. Well, you know, the 9 here tells us that we're uncertain to the hundredths place. The 0 here tells us that we're uncertain to the tenths place. Our answer would then be uncertain in the tenths and the hundredths place. But we can only have one uncertain digit, so it has to be the tenths place. Around the tenths place, it rounds up to 62.1. Okay, so there's going to be a lot of practice with this. We're going to talk about it a lot, but this is a very important rule for you to digest because it's a little different. And again, I think it's a little trickier than the multiplication division. So just make sure that you're kind of aware of that going into it. So here we go. Sample exercise number 12. Go ahead and add the following measured numbers. We have 82.409 milligrams and 22.0 milligrams. And note, you're totally fine. Just use your calculator. So give it a shot. And again, pause the video now. When you come back, we'll have the answer together. Okay, so we're back. I'm going to go ahead and plug this into my calculator. 82.409 plus 22.0. Sure, I could do this login, but we have calculators. So this ends up being 104.409. Well, okay, check it out. Our uncertainty of the first measurement is to the thousandths place. So that's the thousandths place here. The second measurement, 22.0 milligrams, that's uncertain to the tenths place. So that means our answer is uncertain in the tenths place. Now, we can only have one uncertain digit in our answer. So that means that we have to round it to the tenths place here. It's a 0 there, so this should round to 104.4. Let's go ahead and check. Sure enough, we round it to the tenths place. Okay. All right, so those are the rules. Now, this is a good time to take a pause. We're going to have a bunch of practice on this in lab, and I'll post a practice worksheet as well down below, below the sample exercise worksheet. So just keep in mind, oh, before I forget, sample exercises are not due for credit. It's just for practice while you're watching the lecture. It's a way for you to kind of keep track of the problems that you're doing. And then also it's good practice for the tests that are going to be, not necessarily based on those questions, but you'll find some similarities between the test questions and the sample exercises every so often. So it's good for you to practice during the lectures, and that's why I put it in the sample exercise packet. But that'll do it for this lecture. We have one more lecture in this chapter, and then after that, we will be done with chapter 2. So I'll see you then, and I'll see you in lab. And again, make sure, send me an email, comment down below in the discussion on Canvas. If you have any questions whatsoever, I'll get back to you right away. All right, see you soon. Bye-bye.